Hello, this is Devin Rohrbaugh with Applied Flow Technology, and today I will be talking about the As Turbine with Fathom and Impulse. We'll discuss the As Turbine, what it is, what its turbine curve is, its power curve, what it means for it to decouple, and its corresponding no-load curve. We will talk about load rejection and using the As Turbine and Impulse and Fathom XTS. So what is a As Turbine? It's just a pump that is also being used as a turbine to produce electricity. So in its typical pump mode, it's going to be consuming electricity from the motor. That electricity is going to spin the shaft, as you see on the right here. And that spinning shaft is going to spin the impeller, which is going to drive flow through the pump. When you have the pump acting as a As turbine, the opposite process is happening. So you have flow rotating the impeller, and the impeller is then spinning the shaft, which spins the magnets in the motor and produces electricity from the motor as if the motor is a generator. When you use a PAT, you will have a turbine curve, which is this blue curve here. This curve can either be gathered from experimental data, or it can potentially come from a supplier who's supplying a As turbine. We assume that this turbine curve is at a constant speed that we refer to as the rated speed when the As turbine is producing electricity. So at that constant speed, you get this blue curve here. And for a given flow, that blue curve gives you a head loss through the As turbine. You'll notice this dotted section here on the blue curve. This is where the PAT is no longer coupled to the generator, and it would not follow this blue curve in this area. And we'll get to that more in a moment. The PAT also has a power curve, which you can see as this red curve. This is the power that the fluid is enacting on the impeller and applying to the shaft. So this is the power the shaft of the PAT has. However, if you want the exact power you are producing as the electricity, you will have to apply a generator efficiency to this power to get the reduced power that you would see generated as electricity. So you probably noticed that this red power curve hits zero power at a non-zero flow. When this happens, the PAT will decouple. And what that means is the shaft attached to the pump as turbine will decouple from the shaft of the generator. And this is done to avoid hurting the motor that's being used as a generator by allowing it to operate in this dissipation zone. So as soon as the power hits zero and the PAT goes to enter this energy dissipation zone, the PAT will decouple so that the generator is not attached to the PAT while it enters this zone. And this zone dissipates energy because for that constant speed that these curves are on, you would have to have the motor producing power to the PAT again in order to keep it at that speed. So one more thing to note is when you hit this 0 power and the PAT decouples, we cannot model the PAT recoupling currently, but that's something that we might do at a later date. So when your PAT hits that 0 power mark or lower and it decouples, it enters a state that we call free spinning. When the PAT is free spinning, the generator is no longer applying torque to keep it at that constant speed, and the speed of the PAT is directly affected by the fluid. So you can see this equation where we have the new speed, and the new speed for a given time step when you're free spinning is just the old speed minus this equation here, which is a function of the time between the two speeds, the old power, the new power, the old speed, and the new speed. So you could see this as an iterative process to calculate the new speed. And also the new power, since it's at a new speed, it's the power curve adjusted by the affinity laws and the new speed as well. So that's why this is an iterative process for this. But in Impulse, we do this calculation for you to get the to seamlessly get the speed at any given point of time during the transient. And as I mentioned, as the speed changes, the power curve and the turbine curve are adjusted with affinity laws, and then you just use the flow at that point to get the power on that adjusted power curve, and the head loss through the PAT on that adjusted turbine curve, which once again Impulse does for you. So the PAT will continue to speed up in this free spinning state until it hits a runaway speed. At that runaway speed, the flow cannot spin the PAT any faster. So it enters a steady state. So what's kind of happening is you can think of the impeller that's spinning and the flow as like two cars. The impeller is the car in front, and it's just barely being touched by the car behind it. But both cars are going at 60 miles per hour, where the car behind it is the flow. The car behind the car in front cannot impart any force because they're both going at the same speed. But as soon as the car in front goes to slow down a little bit, the car behind it will push it back to make it stay at its same speed. And that's kind of how the runaway speed works. There's no power being imparted on the impeller by the fluid at runaway speed because the impeller is spinning as fast as the flow. But as soon as the impeller tries to slow down at all, the flow pushes on it and makes it stay at that same rotating speed. The last thing to note about runaway speed when decoupling is the PAT operates on the no load curve, which you'll see shortly when it's at runaway speed. So the no load curve is shown on this chart here as this light blue curve that was added. And it represents the steady state at which a decoupled PAT is at runaway speed. So the PAT is only on this curve when at runaway speed and when there is no transient affecting the PAT in the piping system. The no-load curve represents the pressure loss and the flow at which the shaft power is 0. So you can see at this point here, the shaft power is 0. And each point on the no-load curve represents a different runaway speed. So how do you find the no-load curve? Well, for the rated turbine curve and power curve, you take the flow at which the power hits 0, and that gives you the flow for 1 point on your no-load curve. And the head loss on your turbine curve for that flow is the head loss for your no-load curve at that point. So that's how you get 1 point. Then all you do is you just adjust the speed to get a new turbine curve and power curve according to the affinity laws. And then you repeat that process to get a second point. And you adjust the speed again and do that again for a third point, etc., until you have a fleshed out no-load curve. Though one thing that you might notice is the no-load curve is having the head loss proportional to the flow squared, and it's at a 0, 0 point. So understanding that and just taking 1 point from the original turbine curve and power curve, you can calculate out the no-load curve. All right, so what is load rejection? All load rejection is decoupling before the PAT's power hits 0. So this is like a forced decoupling by whoever's running the PAT, or by whatever system is running the PAT. So you can use a Fathom or Impulse to model a load rejection where you can see the power is not hitting 0 yet, but you're decoupling. And the PAT will enter that free spinning state and will eventually steady out to a runaway speed given no other transients. So you can see here in the graph, the PAT starts at 100% rated speed and it decouples right away at time 0. Then it overshoots the runaway speed, then undershoots it, and eventually steadies out at that runaway speed of about 150%. The shaft's power, when you decouple or load reject, will steady out to 0. So you can see that down here on the power curve. Power starts at about 60 kilowatts, decouples at time 0, and the flow is producing positive power on the impeller and shaft until it undershoots 0 here, producing negative power on the shaft. And all that means is the flow is imparting force that wants to slow down the PAT or the shaft. And then it comes up and overshoots 0 a little, making it want to spin a little faster again, and then eventually steadies out at that 0 power, where you can see the PAT is at that runaway speed. So this point at the runaway speed and zero power will match a point on the no-load curve. So when you see where the pressure and the flow has steadied out at this point of time, that point of head loss and flow through the PAT would match a point on the no-load curve. All right, so let's dive into impulse and modeling the PAT in it. The PAT was introduced in Impulse 8. Impulse 8 was already released, but the PAT was added during a maintenance release update in Impulse 8. And the Impulse 9 that's now out has the same exact PAT features as Impulse 8 did. So the key thing about Impulse is it will model the entire load rejection or decoupling. So when you load reject or decouple, you have the free spinning between the steady states of it being coupled and the no load curve, and you have those two steady states. Impulse will model all of that. Impulse also models the decoupling due to the PAT hitting zero power by any cause. So what that means is no matter what you set the transient as in the PAT, Impulse will decouple the PAT when it hits zero power. And that applies even if you have a speed versus time transient in there. It will, during that speed versus time transient, realize it hit zero power, and it will ignore the speed versus time transient that you have set because the PAT is no longer coupled. It is now free spinning and just fully affected only by the flow. So I'll show you what that looks like in Impulse. Here's the pump as turbine, and you can see you enter your turbine curve here and your power curve, and they'll look something like this. In Impulse, you need to enter the speed that the PAT is at while it's coupled and on this turbine curve. And then you can specify the transient. So you have three options for PAT: no transient, speed versus time, or full load rejection. You'll notice that even when you have no transient specified, you still have to input this total rotating inertia. And that's because at any point, even when you do not specify a transient for the PAT itself, it can hit that zero power point and decouple. And when it decouples, it needs the inertia information to model the free spinning of the PAT. So full load rejection can happen at the very beginning, or it can happen due to a trigger. And all that's happening is it decouples when it's triggered, and then it enters that free spinning state. With speed versus time, you enter your speed versus time information for when it's coupled, and the turbine and power curves are adjusted with the affinity laws for the speed you specify. And then at any point, due to the flow and the speed adjusted power curve, the power hits zero, it will stop following what you put on the speed versus time curve, and it will operate as a free spinning turbine. And that's how the PAT is modeled in Impulse. Let's talk about the PAT in Fathom XTS. The PAT was introduced to Fathom XTS in Fathom 12. The key difference between the PAT in Fathom XTS and in Impulse is Fathom XTS can only model steady state snapshots. So since the free spinning is inherently transient, it cannot model that. At any given point in your XTS transient, or in your XTS time simulation, the PAT is either on the turbine curve at rated speed, so that's when it's coupled to the generator, or it's on the no load curve at runaway speed, because like I said, it doesn't model that free spinning in between. Lastly, it can be on the turbine curve, adjusted to the speed that you set in your speed versus time transient. And just like Impulse, if the PAT hits a power at or below 0 for any reason, it will decouple and it will jump to that no load curve. So just like an Impulse, Fathom XTS has the speed versus time option. And just like an Impulse, if you hit the 0 power point during your speed versus time transient, the speed versus time transient will be ignored past that point. And Fathom XTS also offers load rejection. In this case, it load rejects at the first time step. And since it cannot model that free spinning transient, the PAT will start at runaway speed and that no load curve at the very start of your time simulation. Then any point of your time simulation, the PAT will represent a point on the no load curve while it's decoupled. I'll go ahead and show you what that looks like in Fathom XTS. You can see we have our turbine curve entered with our power curve. And once again, that looks like this, where you can see that power curve hitting 0 at a non-zero flow. You do not need the rated speed because we're not modeling the free spinning. So we don't need to know the RPM. And you do not need the inertia anymore because we're not, once again, not modeling that free spinning and we're only modeling steady states. So you have the options of no transient, the speed versus time transient, which adjusts it with the affinity laws. And lastly, the load rejection option, which just decouples it immediately. And that's how the PAT works and is modeled in Fathom and Impulse. Thank you very much for taking the time to listen to my webinar here. Feel free to contact us. You can call this phone number below or email support or sales if you're interested in buying one of our products. And thank you once again. I hope you have a good rest of your day.